What if the universe itself has been misleading us? Not in a symbolic sense, not as poetic language, but in a literal, measurable way, embedded directly in the data. Most people picture the James Webb Space Telescope as a generator of stunning visuals, glowing galaxies, eerie nebulae, cosmic masterpieces. But what Webb is really doing is far more unsettling. It's pushing astronomers toward a possibility they've spent the last century trying not to face, that our most fundamental picture of the universe could be flawed. And this wouldn't be the first time science has been forced into a reckoning like this. Back in 1929, when Edwin Hubble proposed that the universe was expanding, the idea was ridiculed. One well-known physicist allegedly dismissed it as the most absurd claim he had ever heard. The universe wasn't meant to change. It was assumed to be eternal, motionless, unchanging. And yet, Hubble was right. Nearly a century later, astronomers are standing in an uncomfortably familiar place. Once again, the data refuses to cooperate. Once again, the universe is behaving in ways it absolutely shouldn't. Take one of Webb's recent discoveries, an ancient galaxy formed roughly 13 billion years ago, back when the universe was still in its infancy. By all conventional wisdom, a galaxy from that era should be small, chaotic, barely held together by gravity. But Webb revealed a giant. Massive, mature, structured. A galaxy that seemed to have already lived a long, eventful life at a time when the cosmos itself was supposed to still be finding its footing. And this wasn't a one-off anomaly. From the very first weeks of Webb's mission, it began spotting galaxies that were too large, too orderly, too evolved, appearing far too soon. Each observation felt like a warning, a fissure in our understanding of cosmic history. But the real shock wasn't just about the galaxies. It was about the very fabric of space itself. A Nobel Prize-winning physicist recently put the situation in stark, uncomfortable terms. Webb's observations suggest that our understanding of the universe might not just be incomplete or slightly off. It could be fundamentally wrong. At the center of this crisis lies one of the most deeply held assumptions in modern cosmology, that on the largest scales, the universe looks the same in every direction. This idea, known as isotropy, underpins nearly everything we think we know about the cosmos. The Big Bang, dark energy, the cosmic microwave background, they all rely on the notion that the universe is fair and uniform, obeying the same rules everywhere. For decades, the evidence seemed to confirm it. No matter where astronomers looked, the cosmos appeared statistically even. Expansion progressed uniformly. Temperatures balanced. Matter was smoothly distributed. Until now. A paper in the astrophysical journal Letters hit the cosmology community like a bombshell. Astronomers reported evidence that the universe's expansion rate isn't uniform in all directions. Pause and let that sink in. The universe is expanding faster in some directions and slower in others. This isn't a tiny fluctuation, a statistical hiccup, or a quirk of measurement. If it holds up, it means the cosmic clock itself isn't keeping the same time everywhere. And if that's true, almost every calculation we rely on, from the universe's age to its ultimate destiny, comes into question. This isn't a minor disagreement. This is a fundamental challenge to everything we thought we knew. David Gross, Nobel Prize-winning physicist, didn't mince words. This isn't something you'd call a tension or a mere problem, he said. This is a crisis. And crises of this magnitude only arise when something fundamentally has gone wrong. To grasp why this is so explosive, we have to revisit Edwin Hubble's groundbreaking discovery. Hubble observed that distant galaxies were receding from us, and that the farther away a galaxy was, the faster it was moving. In that simple observation lay a profound truth. Space itself is expanding. That insight unlocked everything. If the universe is expanding now, it must have been smaller in the past. That means it had a beginning, an age. And if the expansion occurs at a consistent rate, we should, in principle, be able to calculate that age by measuring how quickly space is stretching. That measurement came to be known as the Hubble constant. From the very beginning, the universe refused to be straightforward. Even before the Hubble Space Telescope took flight, astronomers couldn't settle on a value. Depending on the method used, the universe seemed to range anywhere from under 10 billion years to nearly 20 billion years old. The lower end wasn't just uncomfortable, it was impossible. Some stars appeared older than the universe itself, a clear logical contradiction. Scientists assumed the problem lay in the measurements. Sharper telescopes, more precise data, surely that would reconcile the numbers. But it didn't. The results didn't converge. They split further apart. Today, the debate revolves around two main methods. The first method looks all the way back to the universe's earliest light, the cosmic microwave background. This faint glow is the lingering aftershock of the Big Bang, released when the universe was just 380,000 years old. The Planck satellite measured it with extraordinary precision and arrived at a steady, conservative expansion rate of about 67 kilometers per second per megaparsec. The second method focuses on the nearby universe. It relies on Cepheid variable stars and exploding supernovae, objects whose intrinsic brightness we understand well. By comparing how bright they appear to how bright they truly are, astronomers can calculate their distance and, from that, deduce the current expansion rate of the universe. That measurement comes out significantly higher, around 74. This isn't a rounding error, it's a chasm. For years, astronomers hoped that better data would smooth things out. Instead, the James Webb Space Telescope made the discrepancy even starker. Webb's observations confirmed the Cepheid-based measurements with unprecedented clarity. Adam Rees, Nobel laureate and one of the leaders behind this work, was blunt. Measurement error is no longer a plausible explanation. The universe really is expanding at different rates. And that brings us to a truly unsettling implication. If expansion isn't uniform, then the cosmological principle, the idea that no location in the universe is special, may be wrong. And if that foundation crumbles, everything built upon it starts to wobble. Dark energy, the mysterious force driving the universe's accelerating expansion, suddenly comes under suspicion. We've always assumed it's smooth and constant, but what if it isn't? What if dark energy varies across space, tugging more strongly in some regions and loosening its grip in others? In such a universe, our equations start to unravel. The age of the cosmos becomes uncertain, the scale of reality itself slips from our grasp, and beyond the observable horizon, physics could behave in ways we can barely imagine. Gravity might not always pull, light might not always travel at the same speed, and the universe might not even be consistent with itself. This is why the debates are so heated, why cosmologists are uneasy. This isn't a matter of tweaking a parameter or refining a model. It's about challenging one of the oldest assumptions in science, that we occupy no special place in the cosmos. For centuries, we've held that principle as a cornerstone of modern science. The universe has no center, no preferred direction, no special place. But Webb's discoveries are hinting at something unsettling. Perhaps the universe isn't as impartial as we've believed. Perhaps it never was. And once again, the cosmos seems to be asking a question we're not yet ready to answer. Hit like and subscribe for more updates on our ever-changing universe.